This conference will now be recorded.
Hello and welcome to the Math 136 Final Exam Review A. This video is going to focus on Day 1 material and there'll be a separate video for the Day 2. So we're going to be solving this equation. This is from Unit 4 that we've been working on. And the idea here is that if you can get the same base on each side, then you can set the exponents equal to each other. That's one of our properties. So the goal is to figure out whether or not 64 and 16 can be written with the same base. You cannot make any of the numbers bigger. You can only write it as something to a power. So they both have in common a base 4. So if we rewrite this as 64 is 4 to the third, and then we still have that 3x plus 2 on the outside. And 16 is 4 to the second. And we have an x minus 1 still on the outside. Notice these both are base 4 now. We can distribute this and use the multiplication property for the laws of exponents. So that would make this 4 to the 9x plus 6 equals 4 to the 2x minus 2. So once you have same base on each side, one base just on each side, you set the powers equal. So we set 9x plus 6 equal to 2x minus 2. We're going to try to solve this. So we're going to subtract the 2x over. That would make that 7x plus 6 equals negative 2. We're going to subtract the 6 over to isolate our x. So that's going to be negative 8. And then we divide both sides by 7. So it comes out to an answer of negative 8 over 7. Now, if you're dealing with an exponential equation, it has a domain of all the real numbers. So you do not need to check this on a requirement. Sometimes, remember, we have to do checks because we're required to. You feel free to check, but it is not required for the exponential. So number 2 says, how much money should be invested today in order to have $10,000 in 20 years if the rate is 4.5% compounded monthly? So because they said the words compounded monthly, we're going to be using the formula A equals P parentheses 1 plus R over N and then raised to the NT, where P is the principal or starting amount, R is the rate as a decimal, N is the number of compoundings in a single year, and T is the number of years. So we want to have 10,000. So that means that's our future value. So this is A. The number of years is 20. The rate would be 0.045. You have to divide it by 100 or move the decimal 2 places to the left. So that's our R. And then monthly means 12 times in a year. So let's plug in what we know. So we have 10,000 equals P, because we don't know P, 1 plus 0.045 divided by 12 raised to the 12 times 20. Now you're trying to get P by itself, so you're going to divide this whole parentheses over. Do not try to work this on your calculator piece by piece because you're going to round too soon, too early, and you're going to get the wrong answer. So the only thing I would recommend doing first is you can multiply that exponent together. So this is 12 times 20, so that's going to be 240. So that is 10,000 equals P parentheses 1 plus 0.045 over 12 raised to the 240. We're going to separate that from P by dividing. So 10,000 divided by 1 plus 0.045 over 12 raised to the 240 equals P. So you want to type this into your calculator very carefully. So I'm going to use parentheses just as I see them. So 10,000 divided by, open a parentheses, 1 plus 0.045 divided by 12, close the parentheses, raise it to an exponent of 240. If you don't include this whole thing in parentheses, it will not know what to divide by. And then we hit enter, and that is 4,072, and we always round up for free, regardless of if this tells us to round up or not, because you don't want to undershoot your goal. So it's 4,072 and 55 cents. So 4,072 and 55 cents. So that's the amount we needed to deposit on the first day to have the 10,000 in 20 years. Okay, so for number 3, we're going to be sketching this graph and dashing in any asymptotes, and it is an exponential function. The base is e, so we're going to want to use our calculator. So we're going to make us an XY chart. Now, typically, whatever your center value is, you want this to give you an exponent of 0. So since I have an x plus 3 in my exponent, I'm going to adjust the center of my chart to -3 because I always want that first middle exponent to be an E0 exponent when I work this out. So then you pick two numbers smaller and, or excuse me, larger and two numbers smaller. It doesn't matter which order you pick them in. So let's work this out. So I'm going to write out what these would each be. So this would be e to the -1 plus 3 plus 1. So that's e to the 2 plus 1. E to the -2 plus 3 plus 1 is e to the 1 plus 1. E to the -3 plus 3 plus 1 out here is e to the 0 plus 1. E to the -4 plus 3 and then plus 1 is e to the -1 plus 1. And e to the -5 plus 3 plus the 1 is e to the -2 plus 1. So we want to type in those individual things. So e squared, and I have to do mine kind of backwards, is 7.39 essentially plus the 1. So that's 8.39. E to the first is just e. Sorry, backwards. First power e. And then we want to add 1 to that, so that is 3.72. This is 0 exponents. That's just a 1 plus 1 would be 2. E to the -1. So I have to put my exponent in first on this calculator. And then plus 1 is 1.37. And the -5 guy was e to the -2 when we worked it out. And then plus 1. So that is 1.14. So let's plot at least 3 of our points. I'm actually going to plot all of them. So let's plot 1. Okay, so -1 is at 8.39, so 1, 2, 3, 4, 5, 6, 7, 8, so it's above that. -2 is at 3.72, so that's just a little bit below -4 or +4. -3 is at +2. -4 is at 1.37. And -5 is at 1.14. Notice it's slowing down here towards the 1. That's because when you're doing an exponential graph, your horizontal asymptote is based off that vertical shift. So we're going to ask you, remember, to label that in, dash it in. So at +1, we never get below that line. So that's y equals 1. And then we're going to connect and make the exponential out of the points that we've plotted. Okay, so there's that one. For number 4, we have $5,000 to place in a CD for 5 years. The CD pays 3.6 annual interest compounded continuously. That means we're going to use the PERT formula. How much will the CD be worth at the end of the 5 years? So we know we have $5,000, so that's our initial deposit. The rate was 0.036 as a decimal, and the time is 5 years. The formula A equals P e to the RT. That's what we use for compounding continuously. So we're looking for our future value when we know that we have $5,000. E, remember, is a button on your calculator, so that's going to be our button that we hit, and then 0.036 times 5. Sometimes I will go ahead and work out the exponent before I do anything else, just to make my life a little easier. So that's 0.18, so 5,000 e to the 0.18. So if we type this in, we should be able to find our future value. So e to the 0.18, and then times that by 5,000. That's 5,986.09. Now, it just depends on if you're rounding to the hundredths or the whole number. We didn't specify in here, so I just went ahead and rounded it to 2 decimal places. So if you rounded it, to the nearest whole, you would have rounded it just without the decimal. Okay, for number 5, we want to find the domain, the range, and the asymptote of the given function, and it's a logarithm function. So logarithms have this issue where, remember, if you're dealing with an exponential, you have no domain issues, but then you have a range issue where you have a horizontal asymptote. A logarithm is an inverse of an exponential, so you get a vertical asymptote instead, so you end up getting a domain issue. The issue is that logarithms have to have an argument that is greater than 0. It can't equal 0, it can't be less than 0. So the way you find your domain is you just put the part that is in that parentheses greater than 0 and you solve for x. So x has to be greater than -5. So my domain is -5 to infinity. In a logarithm, it has the domain issues, since the domain has an issue, the range actually doesn't, because remember, it's opposite to the exponentials. So the range will always just be -infinity to infinity. And then the asymptote, a lot of people get confused. They want to use this -1. The asymptote is directly tied to the domain. So the asymptote is a vertical asymptote, x equals -5. Okay, for number 6, we're expressing this as a single logarithm, so we're using our properties of condensing here. So we had the power rule, we have the quotient rule, and the product rule for logarithms. So the first step is to always put the coefficients back inside as powers on the base. So we will do that first. Now this one doesn't have anything but a negative, so we don't have anything to place back there. So this will be log 2 of m to the third minus log 2 base 2 of n to the fourth plus log base 2 of p to the fifth minus log base 2 of q. Okay, so the issue you come into when you're dealing with logarithms is that when you're combining them, we know that subtraction turns into a quotient and adding turns into multiplication. So the problem that a lot of students will run into is when they mix the negatives and positives all together like this, it gets confusing a little bit. So there's a general rule. Essentially, if the log is positive, the base that's inside there is going to be on the top of your fraction. If the log has a negative in front of it, the base is going to move to the bottom. Essentially, it's like a negative exponent. So we're going to have one big log of base 2 with a big parentheses, and this had a positive log, so that m to the third is on top. The negative log base 2 of n to the fourth, that had a negative log, so that n is going to go to the bottom. This one has a positive, so it's going to be on top, and this one has a negative, so it's going to be on the bottom. So we get log base 2 of m to the third, p to the fifth over n to the fourth, q. Okay, for number 7, we're supposed to solve this logarithm equation. Remember that logarithm equations have domain restrictions, so we will have to check all of our solutions. And the rule here is that we have a plus in between these two logs. So the rule is that if you want to combine that to a single log, you turn it into times. So this will be, and they have to have the same base to do that, which they do. It's base e. So then we would have 5x minus 2 times the x minus 1. Those are the two arguments. And then we still have the ln of 5x squared minus 32 on this side. So we need to FOIL out this. That would be 5x squared minus 5x minus 2x plus 2. Natural log of this just comes down. We need to add our like terms in there. So this is 5x squared minus 7x plus 2. Now, because you have one log on both sides and they have the same base, we can set their arguments equal, because if those match, the insides have to match as well. So we're going to solve the two arguments equal to each other. So when we go to solve this, you notice right away that when you try to subtract over, I don't usually show this, but I'm doing it on this one because it's that case where it cancels out on both sides. So you subtract that over and the 5x squareds are both gone. So we are just solving negative 7x plus 2 equals negative 32. Subtract the 2 over, that makes that negative 34. Divide by negative 7. Now, because you get negative on top and bottom, it actually turns out as a positive 34 over 7. Before we can circle that and say, yes, that's good, we need to check each argument. So we're going to take 34 over 7, and we're going to verify that each of these arguments stays greater than 0. So 5x squared minus 32 greater than 0. Okay, so you're going to put these in here for this. And all we care about is it greater than 0? And 5 times 34 over 7 squared minus 32. Okay, so you can use your calculator for this. You just needed to show the work that you're doing the check. So we would do 34 divided by 7 times it by 5 minus 2. Is that greater than 0? Yes, so it works in the first one. 34 divided by 7 is 4.85 minus 1. Still going to be positive, so that's good. Now we want to square the 34 divided by 7, so we get the answer, and then we square it. We times it by the 5, and we subtract the 32. That is also positive. So as long as each argument comes out greater than 0, then we are good. This is a solution. Okay, for number 8, we're also solving a logarithm. We need to combine the two logs that are on the left side. They are again separated by a plus, which means if we're going to try to combine them, we'll be multiplying their insides. So this is log base 3 of x plus 4 times x minus 2 equals the 3. So that's log 3 of x squared plus 4x and minus 2x. I did those kind of in backwards order. And then minus 8 equals 3. Log base 3 of x squared plus 2x minus 8 equals 3. Now, where a lot of times students will go wrong on this problem is they'll just try to set that trinomial equal to 3. That property was only valid if we had logs on both sides. We do not have logs on both sides. We have a log on one side and a number on the other side. The only way you can solve this type is to convert it to exponential form. So this says 3 to what power equals this? And of course, we have the power over here. It's 3 to the third. So 3 to the third equals x squared plus 2x minus 8. So that is 27. We want to subtract that over. So that is 0 equals x squared plus 2x minus 35. We can factor that. It factors into x plus 7, x minus 5. So we have two, we think, possible solutions, negative 7 and 5, but we don't know if they both work. So I'm going to do my check. So over here, I'm going to check it. So I'm going to check negative 7 first, and I have to make sure that both the original arguments, x plus 4 and x minus 2, are greater than 0. If even one of them fails, it's done. It's not an answer. And the very first one fails. That is not true. So negative 7 is not going to make it greater than 0 for the arguments. If we plug in 5, that would be 5 plus 4 greater than 0 and 5 minus 2 greater than 0. Both of those are greater than 0. So 5 is the only solution. Okay, for number 9, you are going to have to try to solve something that has exponential form, but the bases do not match, and they can never match. The problem with this is if you're trying to solve a problem like this, you have to have the exponent base guy, the one right here, it has to be isolated first. So you can't have this times 4 out front, and you cannot times these together. That does not make 20. This has an exponent on it. So the first thing you can do is divide the 4 over and get rid of it. So this is 5 to the 2x equals 6. Again, 5 and 6 will never have the exact base. They cannot have the same base. So one thing we learned is that if you have something where the bases can never match, one trick is to take the logarithm of both sides. Just like when we had two logs on each side, we set their insides equal if they were the same base. As long as you apply the log with the same base to each side, you can do that. Now, what you'll notice is I'm using base 10, so I'm not writing a base on my logs. Now, this frees us up to use the power rule for logs, which says we can take that power and bring it to the front. So that gets the x out of the exponent. That's 2x log of 5 equals log of 6. Okay, so we can divide and get the x by itself now. We'll divide both sides by 2 log 5. Now, they wanted the exact answer and 1 to 2 decimal places. The exact answer is just what you have right here. It has not been worked out. It's just written as x is by itself and everything else is on the other side. To get the decimal approximation, you're going to need to use your calculator. So we will take our calculator and we will do, I have to do my number first. Most calculators, you type log, then the number. So log of 6 divided by, and I'm going to do a parentheses on the bottom, 2 times 5 with a log. All right, so then when we hit enter there, that gives me 0.56. So 0.56. Okay, that leads us into this next one, number 10. This is a little bit more complicated version of that. The problem with this one is that there are bases that can never match, 3 and 5 never match. But why this one's more complicated is because there are x's on both sides in the exponents. So we can use a similar approach. We can take the log of both sides, and we'll pull those powers to the front once we've done that. So I'm going to pull the 2x to the front, so that's 2x times log 3. Be careful when you pull a binomial to the front. It is safer to put it in a parentheses so that you don't lose anything, and then this is just log 5. We need to get all the x terms on one side. Right now that's kind of impossible because this is an x plus 1 times a log 5. So what we do is we distribute that log 5 to both of those terms in that binomial. So that's x log 5 plus 1 times log 5 would just be log 5. Notice that we have two terms that have x, this one and this one. So we're going to move those two terms to the same side together. So we subtract the x log 5 over. The goal of doing that is just like when we were solving literal equations back in Unit 1. We were trying to isolate the x on one side so that we could factor it out. So we'll pull the x out, and that leaves me with a 2 log 3 minus a log 5, parentheses, and then equals the log 5 on the other side. All you have to do to finish this off and get the exact answer is divide by that big parentheses. So this is log 5 from the right side divided by 2 log 3 minus log 5. And that's it. We'll just leave it like that. No approximation asked for. Okay, so now we're at number 11. Tamika borrowed $5,000 at 9% compounded continuously. Find the time required for the amount to double using continuous compounding. So if her money is going to double, that means her future value would be $10,000. So we were plugging in, and this is compounding continuously, so we're using the PERT formula. So 10,000 equals 5,000, e to the 0.09, and we don't know t. Anytime you don't know the exponent, you're probably going to have a good chance of a logarithm being involved. So we're going to first of all divide by 5,000 because you want to get the base that has that t by itself. So that gives me 2 equals e to the 0.09t. Now you can take the log of both sides here, and I would recommend it, except I would use ln because ln is the base that is e. So if we do ln of 2 on this side, we'll do ln of e to the 0.09t on the other side. So that gives me ln of 2 equals natural log of, I'm going to pull that 0.09t to the front, and I still have a natural log of e. What you don't realize there, remember, is that there's a hidden e as that base. So this says e to what power equals itself. It's a 1. Natural log of e is always 1. So really, it just gives you 0.09t. So all you have to do to finish that is divide both sides by 0.09. So let's get our calculator. Natural log of 2 divided by 0.09 is 7.70 years because it said round to 2 decimal places. So the time that it takes for my money to double at that interest rate is about 7.7 years. Okay, number 12 says a drug is eliminated from the body through urine. Suppose that for an initial dose of 75 milligrams, the amount A of t in the body t hours later is given by the formula A of t equals 75 times 0.8 to the t. What is the half-life of the drug? Approximate to 2 decimal places. So the half-life means that we have reached half of our original dose. So if you think about that, you just say, what, 75 cut in half is 37.5. That's our future value. Now, you'll see that this is a pattern. Anytime you have a doubling, you divide and you get a 2. Anytime you have a half-life, when you go to isolate that 0.8 to the t so that you can get rid of the t part up there in the exponent, what you're going to notice is that this is always 1/2. And that's because it's a half-life. So then it doesn't matter if you use ln or log here because there's no e base involved, but I'm just going to take log of both sides. So log of 1/2 equals log of 0.8 to the t. We can bring that t to the front. using our power rule for logs, and we're going to divide log of 1/2 by the log of the 0.8, and that will give me my t. So that's going to be to 2 decimal places. So 1/2 and then logarithm divided by 0.8 logarithm, and that gives me 3.11. And this is in hours, so you do have to use the correct unit of time. Okay, so that's the end of like the Unit 4 material. So the other thing that's going to pop up on the first day of testing is some of the material from Unit 1. So some of these are going to seem like you haven't seen them in a long time, but that's because they were at the very beginning of the semester. So this says simplify, answer only with positive exponents. So it's just using the exponent laws. So 3 times, so there's no exponents on the big outside of the parentheses, so we're okay to go ahead and multiply. So 3 times 5 is 15. X to the negative 10 times x to the 7th. When you multiply bases that have the same base, we add their exponents. So that adds to negative 10 plus 7, so that would be negative 3. Y times y, we add the exponents, so that's 5 plus 2, that's 7. And it did say our answer should only have positive exponents, so we need to move that x to the denominator. So y stays on top with the 15, and the x to the third is in the bottom. For number 14, we are factoring completely. If the polynomial cannot be factored, we will write prime. So this is a trinomial with a leading coefficient that's not a 1, and we can't pull it out as a GCF. So the way I teach these in my class, and I think a lot of instructors do the same thing, is we use the AC method. So this is 3 times negative 8, which is negative 24. And we need to find factors of 24 that are opposite signs since it's negative, and they add to 2, or subtract to 2 if you want to think of it that way. So factors of 24 are 1 and 24, 2 and 12, 3 and 8, and 4 and 6. The only way to make a 2 with opposite signs is to use 4 and 6 and let the 4 be negative and the 6 be positive. Now the next step is not to put those immediately in your factors. That is how you split the middle into 4 terms. So this becomes 3x squared minus 4x plus 6x minus 8. It doesn't matter which one you put where. You can change these around if you want, but you just pull out the GCF for each pair. So this would be an x, which leaves me with a 3x minus 4. This has a positive since it leads with a positive, and it's got a 2 in common, which makes this also 3x minus 4. If the 3x minus 4s are the same, that comes out as a GCF to the front, and then the leftovers or left behinds are the x plus 2. So you can always check yourself on these by refoiling it, but remember the answer is the factored form. Okay, so for number 15, we are doing a fraction divided by another fraction. So we're going to be really multiplying by the reciprocal because we're simplifying this. So we will kick the top and multiply it by the reciprocal of the bottom. I would then recommend factoring anything you can. So on top of the right fraction, that factors into x plus 4 and x minus 4, which means we can cancel out, because this is multiplication, the matching x minus 4s on top and bottom. That leaves me with 3x plus 4 over 4x. That's one way to write the answer. You could also distribute that 3 on top. Okay, for number 16, it says rationalize, which means we want to get radicals out of our denominator. So the way you do that when there's a binomial in the bottom is you use something called the conjugate. The conjugate is the exact same 2 terms, but we change the sign in the middle. So we're going to multiply both top and bottom by the same thing to keep the fraction balanced. So when we FOIL this out, we're going to do square root of x times square root of x is square root of x squared, which means it's just an x. Square root of x times 2 would be a 2 on the square root of x. 2 times square root of x is another 2 on the square root of x. And 2 times 2 is 4. On the bottom, we get square root of x times square root of x, which gives me just an x again. You'll get a plus 2 square root of x, and then a minus 2 square root of x. So those should cancel out. And then we get negative 2 times 2, which is negative 4. So on top, if we combine like terms, we have an x plus a 4 square root of x, because there's like terms right here, and then plus 4. On the bottom, we get x minus 4. You cannot cancel any of this stuff out because it is different types of problems. This is a trinomial, this is a binomial. They do not cross cancel or partial cancel. Also, you have pluses and minuses, so you can't just mark pieces of those out. So let's look at number 17 because we're getting close to the end of part 1. This is solving a rational equation. So the first thing I always do is factor all of my denominators. This factors into x plus 3, x minus 3, and I figure out what my LCD is going to be. Because I clear the LCD out of the fractions, and then I make sure that whatever I solve does not make me divide by 0 in the original problem. So if my LCD is x plus 3, x minus 3, that means that we cannot have an answer of -3 or 3. Both of those would make one of the denominators or more than one of the denominators in the original equation 0. So your first step here is to multiply each term by that LCD. So you're going to write x plus, and as long as you do it to everything on both sides of the equation, you stay balanced. So this is 4x minus 5 over x plus 3, x minus 3. Go for that guy. Then we have our equal sign. Then we do x plus 3, x minus 3 times the second part, which is 2 over x plus 3. So I want you to see the original equation is in the red. And then we have our minus, and then we have x plus 3, x minus 3 again. And that is, I'm running out of room, times the 7 over x minus 3. Okay, in the first one, the whole denominator cancels, so that just leaves me with 4x minus 5. In the second one, the x plus 3's cancel. That leaves me with a 2 times an x minus 3. In the last one, the x minus 3's cancel. That leaves me with a negative for the sign in the middle, a 7, and an x plus 3. You do need to realize this is not an equivalent equation to the original. This is an equation that could have some extraneous solutions because we have cleared those denominators out, which means we've kind of ignored these restricted values. As long as we check at the end, though, to make sure neither one of these is the answer, we will be okay. So then we do 4x minus 5 equals 2x minus 6. Be careful with your negative here. Negative 7x minus 21. Combine like terms on the right side. That makes negative 5x and negative 27. Add the 5x over. I'm going to get 9x. Add the negative 5 over. I'll get negative 22. And then divide by the 9. So notice that is not -3 or 3, so it is okay. Okay, 18 is what we call a work rate problem because you have two people working at different speeds. It takes a girl 55 minutes to deliver the papers on her route. If her brother helps, it only takes 20 minutes. How long would it take her brother to deliver the papers by himself, if necessary, round to 1 decimal place? So the problem with this is that you're trying to compare people who are working at different speeds. So if we could figure out how much of a job they get completed in a single minute, then we could compare them because we have a singular unit of time then. So if the girl takes 55 minutes to deliver her papers on her route, and we're assuming here in our beautiful world of algebra that she's working uniformly, which means she's not stopping for breaks. She works consistently at the same rate the whole time. I know not the real world, but that's what you have to assume to do this problem. So the girl is going to take, if it's 55 minutes, she does 1/55th of the job per minute. So 1 over 55 of the job per minute. Her brother, we don't know what he's doing, so we're going to say that he's 1 over x. So however long it takes him, he does 1 over that of the job per minute. Together, because it says if he helps, that's like I call that the combo, it takes them 1 out of 20 of the job per minute. Okay. Now, when you're setting up this problem, if they're doing the same job, you add the individuals together to equal the combo. The only time we don't do the addition essentially is if you're like doing opposite jobs. Like if I'm filling a pool with one thing and emptying it with the other, then you would subtract because they're opposing each other, but they're both doing the same paper route. So we have to get a LCD to clear out those fractions, or you could just, work this out and then by subtracting the 1 over 55 over, and then cross multiplying. So there's a couple ways you could solve it. My pen just went loco for a second. So, depending on what you want to do, if you want to find an LCD, you can list factors of 55. So that would be 55 times it by 2. That would be what, 110. Still 20 doesn't go into that, so 55 times 3 is 165. 55 times 4 is 220. So it looks like we can use that. So we would have to do 220x because that is our common LCD now, because 20 will also go into 220. So if we multiply each thing in this problem by 220x, we should be able to clear out the fractions and solve. So we know that that went in 4 times, so that leaves me with a 4x. The x's cancel here, so that gives me a 220. And that goes into that, you'll have to excuse me, it is late, 11 times. So that would be 11x. So we would subtract over the 4x, and that would give me 7x. Divide by 7. So 220 divided by 7 comes out to 31.4, since it said round to 1 decimal place. Let me make sure I wrote that right. 31.4. And that's minutes, roughly. So that's what the brother can do by himself. Okay, last two problems. So for number 19, we're doing the people attending the movie and different ticket costs per group. This one can be done with like a system of equations, but we don't usually teach that in 136, so we do it with one variable. So we know that 700 people attended the premiere of a motion picture. Adult tickets cost 9 and children tickets were 4. If the box office receipts totaled 3,400, how many children attended? To make your life easier, let children be X. Number of children. Since there's 700 total people who attended, 700 minus however many children you have is going to be the number of adults. So then you just have to times each of these descriptions by the amount of money that those tickets cost. So children were $4 per child, and adults were $9 per adult, and that equaled 3,400. So we will distribute. That's going to be 6,300 minus 9x equals 3,400. 4x minus 9x on that side would be negative 5x, which is okay because when we subtract, we're going to get a negative number on the other side. So 3,400 minus 6,300. Oops, sorry, did not get that other zero. 3,400 minus 6,300 is negative 2,900. So negative 5x equals negative 2,900. When we divide, that's going to end up being positive, and it's 580 children. And that's all we asked you for. We did not ask you for the number of adults, but if you needed that, you could just say 700 minus the 580. Okay, very last problem on part 1. It says solve using the quadratic formula, so we're being very direct here. So remember, quadratic formula is x equals negative b plus or minus square root b squared minus 4ac all over 2a, where a, b, and c are the coefficients in front of x squared, b, or the x is the b term and c is the constant. You have to be in this format where you're equal to 0 for that to work. But I would highly recommend not plugging this in with the fractions because you're just going to make your life harder. Since this is an equation, you can multiply both sides by an LCD and get rid of those denominators. So 2 and 5 both go into 10. So if we multiply this by 10, half of 10 is 5x squared. That would be 30 and then divided by 5, so that's 6x and negative 30, and that equals still 0. So my a is 5, my b is 6, and my c is negative 30. So x equals negative b plus or minus square root b squared minus 4ac, make sure you get your signs, all over 2a. So 6 squared is 36, working out order of operations. That's 20 and 30, and they're both negative, so I'm just multiplying those three numbers together. So that's going to be positive 600 once we add them together, all over 10. So 600 plus 36 is obviously 636. And we need to ask the question, are there any perfect squares that go into 636? So if we divide it by 6, that's 106. That's not a perfect square. What if we divide it by 36? No. What if we divide it by 16? That's a perfect square. Nope. What if we divide it by 4? Let's think small. Yes. So let's see, that would be 4 times 159. So that's going to be -6 plus or minus 2, because square root of 4 is 2, on the square root of 159, all over 10. And all of the outside numbers are divisible by 2, so you need to reduce that. So if you divide each of these by 2, or imagine pulling a 2 out of them and then reducing it with the 10, that makes this -3 plus or minus the square root of 159 all over 5. Now, just because it is very late and I am tired, I'm going to make sure 159 is not divisible by, it is divisible by 3, but 53 is not. So 53 is not going to work out. So just making sure I broke that down all the way. All right, so you should be able to look through these, and hopefully everyone will do well on their day 1 part of their final. I will be recording the day 2 video shortly and posting that as well.